Hi everyone, it's Jacinta here, one of your Cosmic Savannah hosts. Happy New Year to you all, and thank you for still being here despite the fact that we kind of disappeared suddenly halfway through Season 6. We unfortunately weren't able to continue with the season in 2024, but the good news is that Daniel, Miso and I will be back with you soon, so stay tuned because we're very excited to share the rest of Season 6 with you. In the meantime, I'm very happy to bring you this, let's call it a mid-season special episode, and it's in celebration of a very special event for my research group, because today we have a brand new paper published. It's called, wait for this title, A Spatially Resolved Spectral Analysis of Giant Radio Galaxies with MeerKAT. So that may not sound so interesting, but I hope to convince you that it is. The first author of this paper is Kathleen Charlton, who is my master's student at the University of Cape Town. And this is Kathleen's very first ever scientific publication. And it's my first publication as a supervisor, which means that I go as second author. And so these are quite significant milestones in an academic career that I wanted to share with you. So for anyone who's not familiar with the process, when you do research, the final and some might argue the most important step is publishing the results so that you are sharing your results with the world and then other researchers can see them and compare their results to them. And so that means the research is out there officially. And you do this by writing up a detailed report, which we call a paper, and you submit this paper for publication in a particular journal. So these used to be actual hard copy printed journals, kind of something between a book and a magazine, but nowadays they're mostly just online. And the journal that we submitted our paper to is called the Monthly Notices of the Royal Astronomical Society, which is based in the UK. Now, the editors of the journal then send your submitted manuscript to another expert in the subject who will review your work, and they're called the referee, and they usually stay anonymous, so you don't actually know who it is. They'll take your manuscript, they'll read it through in great detail, and they'll usually make some improvements and suggest some improvements and send it back to you. So you go away and you do those corrections and then you resubmit the corrected version of the paper to the journal. And then hopefully at this stage, the referee says, yep, it's a good paper, and they recommend it to the editor for publication in the journal. So this can be a very long and arduous process because we really have to make sure that every single thing is as perfect as possible. Every single T is crossed and the I's dotted. And this can sometimes take many months or even years. But yes, we finally got the happy news that the paper has been accepted, and then it goes for typesetting into the style of the journal. And at long last, you finally get to the day of publication where it becomes available online via the journal's website. And that's today for us, at long last. The paper is about some research that Kathleen conducted, mostly during her honours research project. And honours is kind of like the bonus fourth year at the end of a Bachelor of Science degree, where you get your first taste of real research. And it's quite rare to get a publication out of your honours work, so Kathleen's done a wonderful job getting this through to a paper, and she's been working on it during her master's, which she's now doing with me, again at the University of Cape Town, while simultaneously working on quite a different project for her master's on something called H1 absorption. So we're going to hear from Kathleen about both of these projects in a moment. It's a chat I had with her a few months ago during a trip to the UK when she just submitted the paper to the journal. So she's going to tell you all about her experiences as a master's student, her adventures in the UK, her master's research on something called H1 absorption, and her new paper on AGN, which stands for active galactic nuclei. So just before we hear from Kathleen, I'll explain a couple of things that will make it hopefully make more sense. So as I've just said, AGN are active galactic nuclei, and these are basically galaxies that are behaving badly and kind of having a rave party powered by a supermassive black hole at their center. And this black hole is kind of feeding on gas and dust and growing bigger. And as it does so, it glows brightly in all different colors in all different parts of the electromagnetic spectrum of light. And Kathleen's new paper is about giant radio galaxies, or GRGs for short. And these are a special type of AGN where the black hole is spewing out enormous jets of this very hot gas called a plasma. And that plasma glows at radio wavelengths. So we can see the plasma jets if we look at them with a radio telescope, which is kind of like, you know, how Superman has X-ray vision. A radio telescope essentially lets us have radio vision. And the jets kind of look like if you stuck two glow sticks into a galaxy where the galaxy was a blob of, I don't know, we call them blue tack. I think some people call them sticky tack. If you stick two glue sticks in either side and had them pointing out at either end, that's kind of like what the radio jets look like. And then if you kind of rip off the end of the plastic of the glow sticks and you kind of wave it around a bit so that the glowing stuff sprays out, that's kind of what it looks like at the end of these plasma jets. Okay, I'm not sure that my attempt to link the rave party analogy with the glow sticks is working very well. I think Dan and Sia are going to have a field day teasing me when they hear this. But anyway, a giant radio galaxy is when the glow sticks, i.e. the plasma jets, are really, really huge. And in Kathleen's paper, she actually studies 3 of these giant radio galaxies, which are actually quite rare. And she tries to figure out how old they are. We don't really know that much about giant radio galaxies at the moment because until recently we hadn't found very many and we didn't have good enough data to kind of really study the physics of what's going on in them. And so that's what Kathleen is actually doing in this paper for one of the first times, and certainly with the best resolution, using South Africa's very powerful radio telescope called MeerKAT. So one of the giant radio galaxies, or GRGs, that she's looking at actually hadn't been found before. And so she presents it, the discovery, for the very first time in her paper. We had to give it a very boring catalogue name in the paper of MGTC J1022.85 plus 03152.0.4, which is long even to type. So we called it a boring nickname in the paper called GRG3. But since then, Kathleen's given it a more public nickname of Inkathazo, which means trouble in the Xhosa and Zulu languages, or isiXhosa and isiZulu African languages. And I'll explain why she gave it that name afterwards, but for now, why don't we hear from Kathleen when I spoke to her at the University of Oxford just a few days after she had submitted her paper to the journal. With us now is Kathleen Charlton. Welcome to the Cosmic Savannah, Kathleen.
Hi, thank you for having me on.
Kathleen, tell our listeners a little bit about who you are, where you're from, what you do.
Oh, hi everyone. I'm a current first-year master's student working with Jacinta at the University of Cape Town. I'm originally from Johannesburg, but yeah, I did my undergrad and now my honours and masters in the University of Cape Town.
And how are you enjoying that?
Oh, I'm loving it. I mean, don't tell Jacinta, but I think she's a good supervisor.
You have to say that.
Definitely don't know.
Okay, so Kathleen, you and I are sitting here in a nice office in Oxford at the University of Oxford, astronomy department. Why are you here?
Well, I have a great supervisor who managed to get us a grant to get us to come and visit Oxford so that I can collaborate with 2 of my other supervisors who work here in the department.
Full marks for you. Okay, so let's start off with your research. What are you working on for your, well, obviously I know what you're working on for your master's, but tell our listeners a little bit about what you do.
I work a lot in radio astronomy, mainly in galaxy evolution. So what I'm doing is I'm looking at the neutral hydrogen content within galaxies. I do this looking at the H1 absorption, so H1 neutral hydrogen, so it's very cold gas that we find in and around galaxies. And when we have a supermassive black hole at the center of these galaxies that's actively accreting matter, then that matter then gets ejected, and then that causes outflows and lots of like dynamical movement within the gas in these galaxies. And so I'm looking for outflows and inflows and essentially movement of this neutral hydrogen gas in these active galaxies with the MeerKAT telescope.
So you're looking for gas flowing around and being blown out and sucked in and all of this stuff in a galaxy that has a supermassive black hole at the center that is eating stuff.
Essentially, yes. Yeah. Very complicated, essentially. But what it really is it's looking for dips in light spectra. So yeah, cool stuff, but very simple to look at.
What does it look like?
Well, essentially you have, in the radio, you have a certain wide band. So you're looking at different frequencies. Imagine the electromagnetic spectrum, right? So you've got the different frequencies and they all represent different parts of physics. And so neutral hydrogen essentially eats and absorbs the light at a certain frequency, which we know is the 21 centimeter line. That is at 1,420 megahertz. So then if I look at the sky at a frequency band that includes 1,420 megahertz in it, and I see a dip in the light spectrum, then I know that there's hydrogen gas there because the hydrogen gas is absorbing the light at that frequency.
So it basically looks like a wiggly line with a dip in the wiggle.
Exactly. Yeah. Much less pretty than all the pretty pictures that we see, but it's still interesting and can tell us a lot about the physics. Depending on how broad the line is, you can see how much it's moving. Depending on how deep the line is, we can determine the column density, which tells us how dense and how much gas there is in the galaxy. We can determine the velocity of the gas. Is it moving towards the galaxy? Is it moving towards us? Lots of things that we can determine from this little wiggle, essentially.
Yeah, it's really amazing how much information we can get on a galaxy that's billions of light years away from a little dip and a wiggle line. So it's really cool. So have you found any of these what we call absorption lines yet?
I have. I've got a sample of around 180 galaxies that I'm looking at. I think I've got about 13 candidates that I'm actually quite excited about, but we'll have to do follow-up research and look at the properties of these lines to really kind of hone in on what we're seeing.
So you found 14 dips in some little dips in some spectra, in some lines that you think are real dips, real absorption lines, telling us the real signature of hydrogen.
Well, yeah, according to my supervisors, and then I'll have to get the confirmation that this is real. But I think they're real. I've got to convince them that it is real.
Good challenge. So, what are you working on here in Oxford now?
So as I mentioned about my supervisors, it's really kind of coming to the sources of these information. So my two co-supervisors are Dr. Ian Hayward and Professor Matt Jarvis, who both work here at Oxford. And they both work on the South African radio telescopes, but they also have a lot more knowledge about radio astronomy in general. And so then I'm coming here to really collaborate and learn from them about the deeper ideas around radio astronomy and around H1 gas, and really just soak up as much as I can. Also to see how a different department works and how astronomy works internationally here in Europe.
And how do you like it here?
Definitely the weather is better in South Africa. But oh my gosh, it's absolutely amazing to kind of, I feel like I've learned so much just like kind of getting into a room with these people and just talking to people. Especially as a master's student, it's very easy to be intimidated. And you have these big names. And I mean, Oxford is a very well-known household name. It's not something trivial at all. But getting to come and actually speak to these people and like learn from them, it's a mind-blowing experience. And I'm very lucky and I'm very privileged to do that.
And just walking down the corridor, you meet some pretty big names, right?
Just today, just before this, Jacinta introduced me to Jocelyn Bell, who, oh gosh.
Kathleen's speechless and trembling.
Oh my gosh, no, I mean, when you read all these papers about these amazing people who've literally been pioneers in physics and astronomy, and as women astronomers, when usually like put in the back to run the numbers, it's really, really cool. So Jocelyn Bell has been fundamental in pulsar work, which is not really what I do, but it's something that I've learned about in textbooks. So it's really cool to just sit and have a conversation with her.
Yeah, and we actually had a episode with Jocelyn in season 5, so you should go and check that out if you haven't heard it already. And as Kathleen said, she discovered pulsars basically. And what do you think of the town of Oxford?
Oh, it's so beautiful. I mean, South Africa has got many natural beauty elements, but a lot of the buildings are so new. Our history, our current history is very new compared to Oxford, where you've got the records, at least, of these buildings from like 1,000 years ago, and you can really see it in the town. It's very different from what I'm used to, but I've just been walking around, going and seeing the libraries, seeing all the colleges. Oh, yeah, and just like kind of soaking up the feelings of it all.
And you've actually been in the UK for a couple of weeks now. Where were you before Oxford?
I also got the opportunity to go and present at a conference in Durham called Aegean Populations Across Continents and Cosmic Time. Your mouthful of a name, but it was a very cool collaboration between lots of African astronomers and more European astronomers, and from people all over the world, but like really focusing in and honing in on African participants and African astronomers, and talking about AGN, which we know are active galactic nuclei, which essentially are the galaxies that are active and accreting matter onto their supermassive black holes. And it had some of the lead people and astronomers in the field literally talking there. Lots of review sessions, lots of collaboration sessions, like networking, also help sessions. There was a buddy-buddy system, so I got paired with a senior PhD and got to talk to her about the process and about like how she was finding her PhD. Oh my gosh, I think I learnt more last week than I've learnt in a long time. I think I'm still processing, but it was really, really cool. Also seeing a different part of England really highlights the differences of England. I mean, we think of it as this tiny little island, and no, they are completely different places, but also very beautiful town, also very old town, historical town, and just what an experience to be able to go and learn from the best.
Yeah, so cool. I was there at the Durham conference as well. And of course, Durham is up in the north of England, and Oxford's kind of in the middle south-ish thing. Don't quote me on that. Sorry for my British geography. I also thought it was like such an amazing conference. How did you feel now that you've been to a big international conference in person and, being here in Oxford, meeting with your supervisors in person? How do you feel about that compared to like online meetings on Zoom, which, we're really lucky we can do. But I think, how do you feel do you feel like it makes a difference in person?
Yeah, I think I'm very qualified to kind of talk about this because I completed my undergrad and did quite a bit of my honors online because of COVID. I mean, and it was amazing that I could still do research and learn so much while being shut up in my room. Actually, for the first part of my research with Jacinta, she was in Australia, I was in South Africa, and we hadn't met, and we did all of our research together, and we managed pretty well, but there's something different about it being in person. I think just things happen so much faster. Also, like a lot of new collaborations form, new ideas form when you're in person because there's much more organic, natural atmosphere, and it's infectious and it builds, and then you're literally with so many great minds, and then people just build on ideas. And I think on Zoom, we tend to kind of try and focus as much as we can on just getting it done and then leaving the meeting. Also, there's not as much of that human element, the little small talk, the little like, who are you? Like, how are you? Like, what's going on? I just think a lot is missed. I think it is a valuable tool that we can use, but I think it needs to happen in conjunction with in-person meetings. I've learned so much and I've gotten so much done in the last 2 weeks. Yeah, it's been crazy productive. So helpful.
Speaking of productive, you've actually just submitted your very first research paper to a journal publication last week during the conference. Super productive. So congratulations on that. And that was from your honours research, which you did with me, as you just said, entirely virtually from Australia because of COVID and visa issues and all that jazz. And that was on a very, very different topic to your master's. So congratulations. And can you tell our listeners a little bit about that research?
I mean, it was very lucky that I was able to then go to this conference, literally talking with collaborators just before submitting, which was super, super helpful. So this was work that I did with Jacinta on giant radio galaxies. So also in the radio regime, essentially looking at the largest radio galaxies that we see. So these are massive, massive structures, over 700 kiloparsec I don't know if you know Star Wars, but it's a long distance, okay? It's a massive, massive distance.
Not a speed.
No, definitely not a speed. So essentially these are massive galaxies that have got emission of relativistic electrons that have been pushed from the center of the galaxy into these giant plumes, and they interact with the surrounding environment, which is the emptiness of great space. There is not nothing there, but which is why we call it environment, but it's going out into the furthest reaches of what we can kind of conceive as to be a galaxy. And so, yeah, I was looking at how old these galaxies are, because we wanted to figure out why these galaxies grow so big, what's causing it. Is it the fact that they're just super powerful? Is it that they live in very low density environments, which means that they can go further? Or is it just that they're just super old and that's like what's allowed them to get that big? And so I was looking into the ages and comparing it with simulations, and essentially it's still very complicated.
Yeah, it is very complicated, and you've done a fantastic job in trying to analyze all of that. And that was actually a follow-up piece of research to a paper that I published in 2021, and I think I spoke about it on this podcast. I think it was episode 35, but don't quote me on that. I'm going to fact check it. So it's really exciting that you've managed to do the follow-up research on that. And that was also using MeerKAT, right?
Yes. So it was, so your work was in L-band, which is that one frequency that you looked at the giant radio galaxies. And then you did a follow-up at a different frequency, at a lower frequency. And then looked at these galaxies at this different wavelength. And I compared the brightness at these two frequencies because of the physics of the relativistic electrons. From that, you can deduce how long ago they were accelerated or how long ago they were given energy, which essentially is a complicated way of saying how old they are. So then you can determine how old the different parts of the galaxy are, which is really interesting to determine how it's evolved over time. And that's what you then compare to simulations and kind of say, okay, well, according to simulations, it should be around 900 mega years old. According to what I've got, it's around 70 mega years old. That doesn't agree. Why is that? And go from there.
Right. So, and as you said earlier, we want to know the age of these radio jets, of these giant radio galaxies, because we want to understand how they got so big. And is it just that they're the oldest of the oldest? In which case, as you said, the relativistic electrons, the electrons that are traveling close to the speed of light, should have been doing that for a longer time, but it's really complicated to figure out how long. And this is called spectral aging, one method of doing that, right?
Yes, the whole kind of process is called like spectral index, spectral analysis, and then from that you get spectral aging, looking at the time since the electrons were last injected with energy, so the last time they were kind of sped up.
And this is actually the very first paper to come out of our research group, which we call Radiance. How was the experience of actually writing up a paper? Be honest.
A lot longer and than I thought. What's very good, I think, also because I'm very junior, I mean, as we said, this is my first paper and the first paper of Radiance, is that you want to get as many good comments from as many people as possible. Doesn't help when you put your life and soul into something and then give it up to somebody more senior and then they just come back with red marks all across the page. But apparently that happens to everyone. So,
Literally everyone. And it's a gift. Our comments are a gift, Kathleen. It's not destroying your paper.
Yeah, oh my gosh. So the paper writing process is incredibly long and arduous because you want to make sure that you're getting everything right, that everything's as perfect as you can make it, that you're justifying literally everything that you do. No stone can be left unturned. Essentially, I write it, I give it to Jacinta, she comes back, gives me comments, I rewrite it, give it to Jacinta, she gives me comments, I write it, but then we open it up. So I work, both Jacinta and I work with a collaboration on the MIGHTEE survey, which is essentially the radio data where these GRGs were originally found and what then Jacinta used in her paper that she wrote up with the rest of the MIGHTEE team. And so then I collaborated with all of them. So then all of them had to come back and give me comments, and then I had to include them, probably redo the research a few times, kind of change a few parameters, tweak a few things, make sure I'm doing everything right, give it back to them. They give me more comments, and then I sit with Jacinta going like, okay, can we please submit this now? Can we please submit this now? Can we please submit this now? And she's like, no, it will be perfect. And then we submit, and then now we hope and we hold out for the referee. So the publication that we have submitted to is one that is peer reviewed, which means that nobody can just submit something and say, this is science. You have to get another expert to then come and critique and say, yes, no, this is correct science. They haven't just put out nonsense. So we're waiting to hear back from them. And then if they've got any changes, we'll implement those. And then it'll hopefully go in the journal.
Fingers crossed. So yeah, it is an extreme exercise in patience and perseverance, and you've done very well to get to this point, and I'll be updating our listeners as to when it gets accepted in the future. Thank you very much for spending some of your precious Oxford time with us, speaking with us today, Kathleen. Do you have any final messages for listeners?
Just saying that what I get to do is an extreme privilege, and I say that like astronomy is... It's something that is universally loved and adored. Like, we all look up at the same sky, and it's amazing that I get to do this for a living. I get to just ask questions and learn for a living.
Yeah, I agree. We complain sometimes, but actually it's really cool what we get to do.
Yeah, and being able to work with people from all around the world who all share the same passions that I do. Really cool.
Absolutely. Thanks very much, Kathleen.
Thank you for having me once again. I love this podcast.
Woo! Well, I already kind of ruined the surprise, but the update is, of course, that Kathleen's paper has indeed been accepted and has been published today. So a huge congratulations to Kathleen. It's a really enormous achievement, especially at this early stage of her career, and very well deserved after a huge amount of effort that she put in. We've also put out a press release about this publication today. We can link to in the show notes, along with some beautiful images of the Inkathazo radio galaxy that Kathleen has made. Really some beautiful images. And you can see what I mean by the glow sticks, although I don't think you'll really be able to see glow sticks in this image. You'll probably think it's a ridiculous analogy, but I'll leave it up to you to judge. So yes, as I mentioned, Kathleen has given the new GRG she discovered a nickname, Inkathazo, meaning trouble in isiXhosa and isiZulu. And she called it that because it doesn't have some of the same characteristics as other GRGs. So it gave us a lot of trouble trying to analyze it and understand the plasma physics of what's going on. So for example, one of the plasma glow stick jets is kind of bent. And most GRGs have these jets that are kind of straight across from end to end. And another strange thing is that this GRG is actually living at the center of a cluster of galaxies, whereas we usually find GRGs kind of on their own in galaxies that are quite isolated from other galaxies. And we think that's usually because we need the surrounding environment or the density of the stuff between galaxies to be quite low in order for those plasma jets to be able to propagate, to grow out to very large distances. You can imagine that if you're huddled in a group of people, it's hard to spread your arms out very far without hitting some of the people. And that's kind of what we think it's like for GRGs. If they're very far away from all other galaxies, they can spread out to large distances. But if they're in the cluster, we're quite surprised that one would grow there because it shouldn't really be able to grow out to such big sizes. And in Inkathazo, it's actually, the jets are more than 3 million light years from end to end. And that's about, to give you some scale, about 32 times the size of the Milky Way, which is really enormous. So this is a bit of a puzzle. And as Kathleen said, she used MeerKAT to make what we call spectral age maps of the 3 GRGs that she looked at. And these tell us about the age of the plasma in different parts of the jet. So kind of how long it's been since the electrons within this plasma hot gas were, kicked up to speeds that are relativistic, meaning close to the speed of light. And with MeerKAT, Kathleen was able to make some of the highest resolution age maps of GRGs, just because of how good MeerKAT's resolution and sensitivity is. And so 2 of the GRGs she studied, their age maps were relatively well behaved, and they kind of look how we expect them to look. And these 2 are actually the ones that I published in a paper in 2021, and I talk about in episode 31. I said when I chatted to Kathleen, episode 35, that was incorrect. It's actually episode 31 if you want to go and have a look. But the age map of Inkathazo looked really strange, hence why it was trouble. But it's always exciting when we find something that we don't expect, that doesn't fit into our models, because this is where we have an opportunity to study some new physics potentially. What's probably going on here is that the electrons in the plasma jets might be getting some energy boosts when they interact and collide with hot gas in the intracluster medium, meaning this hot gas that's between galaxies in a cluster. And since GRGs are usually kind of born out in isolation where you don't have this intracluster gas, then we usually wouldn't see these strange energy boosting effects. So this might be some new physics. It might give us some important clues about, how GRGs and galaxies in general form and evolve. And that's what we'll be working on more in the future. And the other exciting thing is that I mentioned that we previously thought that GRGs were rare. The first one was found in the 1970s, and over the following up to 50 years, up until 2020, only about 800 of them have been found in the whole sky, despite the fact that we knew of millions of kind of smaller sized radio galaxies. Yet in the last 5 years alone, more than 11,000 GRGs have been found, which is incredible. So this research field is really heating up. It's very exciting. It's changing rapidly, almost too rapidly to keep up with. And so it's very exciting for us to be right in the thick of it. But most of these sort of 11,000 GRGs are in the Northern Hemisphere, high up in the Northern Hemisphere, because there's a telescope in Europe called LOFAR, which is also very good at hunting for these objects. But there's probably the same amount of GRGs in the Southern Hemisphere, this treasure trove of undiscovered GRGs. What we need then is a telescope capable of detecting them that's in the Southern Hemisphere, which of course is what MeerKAT is. And so Kathleen's paper and my paper from 2021 and a few other papers, they're really proving how good MeerKAT is at being able to find these objects. And then, in addition to that, of course, there will be the SKA in the future, the Square Kilometre Array Telescope. It's already being constructed in both South Africa and Australia, and that should even blow us away even more with what it finds and how many giant radio galaxies it can find and how many unknown things it can find. So I think that's it for today. I think I've talked your head off about giant radio galaxies a lot. I hope you're as excited about them as I am now. Before we go, I just want to give a shout out to Associate Professor Kshitij Thorat from the University of Pretoria, who co-supervised Kathleen's honours research project, and the other members of the MIGHTEE and UHF Cosmos teams who co-authored the work. And finally to the Africa Oxford Initiative, who sponsored our research trip to Oxford. So we hope you'll join us again soon on the Cosmic Savannah as we continue with Season 6. Bye for now.